Hello, I'm SeungWon Seo. Today I will talk about WorldCoder, a model-based LLM agent that builds world model by writing code. Before going into the paper itself, I will briefly explain why world model matter and how the field moved from neural world model to LLM-based world model and then to code world model. A world model is simply an internal simulator. Given the current state and an action, it predicts what may happen next. This is useful because an agent can think before it acts instead of learning only by expensive trial and error. The first major direction is neural world model. Here the environment dynamics are stored in neural network weight. This model compresses observation into latent state, which are hidden vector, and then predict future state or reward. This idea has been very influential in model-based reinforcement learning, from early world model to systems like Muzero and Dreamer series. The benefit is that neural models can handle low sensory inputs such as image, but the downside is that their knowledge is hard to inspect, hard to edit, and often expensive to learn from interaction data. The next idea is to use an LLM as the world model. This became attractive because LLM already contain a large amount of world knowledge and can understand natural language code. Some methods ask the LLM to directly predict next state, evaluate action, or even guide research. This is powerful in low data setting. However, there are also clear problems. The LLM may be inconsistent across steps. It may hallucinate transitions that are not actually valid, and if we query it at every action, the computational costs grow quickly. This motivates code world model. Instead of keeping the world model only inside neural weight or only inside text prompt, we represent it as executable code. The LLM is used to write and debug that code. Then a normal planner can run on top of it. This has several advantages. Code is explicit, so we can inspect it. It is executable, so it is more stable than freeform text generation. It is also editable, which makes transfer easier. The key message of this paper is simple. The LLM should not simulate the world directly. It should build a simulation of the world. Now, let us move to the paper itself. The paper is called WorldCoder, a model-based LLM agent building world model by writing code and interacting with the environment. The goal is to let an agent learn how the world works by collecting experience, writing that knowledge into Python code, and then planning with the learned code. The author positioned this method between deep model-based reinforcement learning and LLM agent. Their claim is that it can run with fewer interactions than deep RL, use fewer LLM calls than React-style LLM agent, and transfer knowledge by editing code. To keep the problem manageable, the paper studied deterministic environment. Deterministic means the same action in the same state lead to the same result. The goal is given in natural language, such as open the door or pick up the box. Instead of raw pixel, the state is represented symbolically as object and attribute. For example, we may have a door, a key, and an agent, each with location and properties. The world model is implemented as two Python functions, one for state transition, meaning how the world changes after an action, and one for reward, meaning when the goal is achieved. This separation makes the representation easier to reuse and debug. The first requirement is quite intuitive. The learned code should explain past experience. The agent stores tuple of state, action, next state, reward, and goal. You can think of this as a dataset of transition collected from interaction. Then the LLM proposes Python code that tries to reproduce this transition. Importantly, this code is not just generated, it is actually executed and tested against the data. If the code fails on some trajectory, meaning it predicts the wrong next state or reward, that failure case is fed back to the LLM and the code is revised. So this becomes an iterative loop of proposing testing, and fixing. This is very different from standard neural world model, where we train parameters using gradient descent. Here, we directly synthesize a program that explains the data. In simple terms, the system writes a hypothesis about how the world works, test it against experience, and fix the mistake step by step. The second requirement is the core novelty of the paper. Among all world models that fit the current data, the agent prefers one that still suggests some rewarding path if possible. This is called optimism under uncertainty. The key idea is that there can be multiple programs that explain the same past experience. Instead of choosing a conservative one, the agent selects a model where success is still achievable. For example, if the agent is unsure whether a door can be opened, an optimistic model assumes that it might be possible and plans action that try to open it. This encourages the agent to explore action that could lead to success rather than getting stuck with a pessimistic model that blocks all progress. As a result, exploration becomes goal-directed instead of random. In the full loop, the agent collects interaction synthesizes code, planned with the code using a planner, which is a search procedure over future action, act in the environment, and then use new counterexample to refine the code again. Another important detail is refinement. The LLM is not expected to write a perfect program in one shot. Instead, it repeatedly debugs an existing program using example it cannot yet explain. So the process becomes write code, test it, find failure, and fix them. This is practical because many environment rules appear as corner case, and it is much easier to extend a partial program than to generate a perfect one from scratch. This is also very different from standard reinforcement learning, where adapting to a new environment often requires retraining a policy from large amount of data. Here knowledge is explicitly stored in code, so for transfer, the agent does not start from nothing. It edits the existing program. For example, new dynamics can be handled by modifying the transition function, while new goal can often be handled by updating the reward function. In that sense, knowledge transfer looks like program editing rather than retraining a new policy from scratch. Let us now look at the result. In Sokoban, the agent starts with only the natural language goal win the game. From the first 50 actions, it runs a human readable world model. The run code generalized to level with more boxes and even adapt to a modified version with teleport gate. This is important because it shows the system is not just memorizing a fixed rule set. The paper also compares against React and DeepRL. React has the same pre-trained LLM knowledge but performs poorly, and DeepRL needs over 1 million steps for a basic 2-box setting. WorldCoder pays the LLM cost upfront, then plan mostly through code. In Minigrid, the paper studies transfer more directly. When the new environment introduces new object or new dynamics, the agent extends the existing code with a few more interactions. When the environment is the same but the natural language goal change, it can often update the reward model with zero additional environment running. This is a very clean demonstration of why explicit world models are useful. In AlphaWorld, the setting becomes much more complex. Even there, the system can synthesize world model with over 250 lines of code and handle tasks like pick and place, hit and place, and cool and place. To conclude, I think this paper is interesting for 3 reasons. First, it treats code as a world model rather than it's just a tool for solving coding tasks. Second, it shows a useful division of labor. The LLM write and repair the simulator, while a planner search over action. Third, it makes transfer much more tangible because knowledge can be read and editable. At the same time, there are clear limitations. The environments are deterministic, the states are symbolic and discrete, and the method does not yet bridge all the way from raw perception to real-world embodied control. Still, as a research direction, code world model feel like a promising bridge between LLM prior and model-based planning. Thank you for watching this.